Take a walk through any modern city, and you are moving through a dense, chaotic sea. The empty air around you is packed with data. Millions of devices are operating simultaneously. Yet the GPS data guiding your phone doesn't crash into the local rock station, and your cellular call doesn't bleed into a passing taxi's dispatch radio. To understand how we keep these invisible signals from scrambling each other, we have to look at the physics of how they are created in the first place. This massive communication infrastructure relies on a specific physical event happening inside every antenna on Earth. We can see this by looking deep inside the metal of a single broadcast wire. An electrical charge that is sitting perfectly still, or even flowing at a steady, uniform speed, cannot produce a radio wave. The space around it remains quiet. But when you force that charge to accelerate, rapidly bouncing it back and forth, it generates an electromagnetic wave that radiates outward through space. Notice what happens as this charge speeds up. The faster the electron bounces, the shorter the distance between the peaks of the resulting wave. This rate of oscillation determines the wave's frequency. By controlling exactly how fast these electrons accelerate, we create distinct frequencies. These function like isolated lanes on an invisible highway, keeping signals neatly separated in the air. This timeline shows the radio wave portion of the electromagnetic spectrum, ranging from 500 kHz on the left to 1000 MHz on the right. The lowest lane on this highway is the AM band, which sits between 530 and 1710 kHz. Because these waves oscillate relatively slowly, they have very long wavelengths, sometimes hundreds of meters. These long waves can bend around large obstacles like hills, which allowed early broadcasts to reach family radios across immense distances. Moving up the timeline, the frequencies stretching past the AM band up to 54 MHz are reserved for shortwave radio. Organizing the lower end of the spectrum into these distinct frequency ranges allowed early global audio communication to scale without overlapping. While audio is a relatively thin stream of data, a moving picture requires millions of bits of information every second. To carry that load, broadcasters use higher frequencies, which provide more cycles per second to encode complex visual details. This chart shows the massive block of spectrum stretching from 54 to 890 MHz. This expanded bandwidth accommodates the high data density of television waves. Nested right inside that television block is the FM radio band, operating between 88 and 108 MHz. Utilizing these higher frequencies allowed for the transmission of the complex data streams that defined the era of household television. Beyond the TV and FM ranges lies the ultra-high frequency, or UHF band. Cellular phones utilize the UHF band to transmit the two-way voice communication we rely on today. Climbing this ladder from the kilohertz to the megahertz ranges opened up the wider lanes necessary to carry the dense data of the modern world. This map shows how AM, FM, TV, and UHF function as neighboring but distinct territories on the same electromagnetic highway. Every signal on this map is generated by the same physical phenomenon, the accelerated motion of electrical charges. These massive fields of broadcasting towers are designed to force electrons to oscillate at highly specific, timed intervals to broadcast information across the globe. Whether you are tuning a vintage radio or answering a smartphone, the technology relies entirely on our ability to control the acceleration of an electron to organize and broadcast energy through space.